students, the topic torque is not yet complete, and today in the line are two more things associated with torque. One is work done by the torque and other is power developed by the torque. So now I am going to discuss these two terms and then we'll solve few questions based on these. So let's get started. Work done by a torque. Already we have studied about work done by a force. So even by analog we can say that what will be work done by a torque. But let us understand it properly. So here I am deriving a situation. These are the x and y axis. It is the origin. Let that be C. Here is a point P1. Position of this point is R1. And it is at angle theta with the x-axis. Now if it gets displaced to another point, let that be P2. The time interval I have considered to be very small, and let this small differential angle be equal to d theta. Now this small displacement can be written as ds, and I am considering that application of force is in this direction, that is F1, which is making an angle. If I extend R1, this angle is equal to alpha 1, and the angle that F1 is making with ds has to be tangential, so this angle is phi. So these are the situations that I have drawn here. Now if we consider torque of force F1 which is acting on the particle P1, now if we consider that the particle at P1 is describing a circular path, radius of which is R1, of course it will be easier to derive then if we consider path to be circular. So then C will be at the center, and we can write radius of path has to be equal to, that is CP1, and its value as it is shown here is equal to R1. Now in time delta t, the point has moved to another position that I have shown here by P2, and displacement is ds. Therefore magnitude of ds can be written as it is the arc, so that will be equal to R1 d theta. And of course its direction has to be tangent to the path. So if we calculate work done by the force on particle, that work done can be written as, I am denoting by dW1 because it is a small differential work. So dW1 can be written as F1 dot ds. As you know, work done can be calculated by dot product of force with the displacement. So it will give F1 ds cos phi, as angle between ds and F1 is shown phi here. So it will be equal to F1 ds cos phi. Now this ds can be substituted from above. So this will be F1 R1 d theta cos phi. Also it can be written as F1 R1 d theta cos phi can be written as cos 90 minus alpha 1, because alpha 1 is the angle that force is making with R1. So phi can be written as 90 minus alpha 1. What this value is now? F1 R1 sin alpha 1 d theta. Next if we consider effective torque due to F1, so this torque can be written as, it will be CP1 because it has to be R cross F. So this will be CP1 cross F1. What is this value now? It can be written as R1 F1 into sin alpha 1. Here I have written only the magnitude of torque. Now if I substitute this value here, it will be reduced to, because F1 R1 sin alpha 1 can be written as torque. So that will be tau1 d theta. This is work done by the force F1, as you can see, and from here now we can generalize the result, because if only one force is acting, we will write dW is equal to tau d theta. But if so many forces are acting on a particle or a system of particles, then of course we have to write for each force independently, and we can generalize the term dW to be equal to tau d theta. And of course on integration this will give net work done to be equal to integration of tau d theta. So this is work done by a torque. As you can see, even from analog we can write, because work done by a force is written as integration of F ds. So here we have to replace F with torque and ds with d theta, and we will get the similar result. This is work done by a torque. Now let us come to the power developed by a torque. So here it is. Now since power can be defined as, its mathematical definition can be given as dW upon dt. So if I now substitute the value of dW, because already we have just now derived it, so it will be tau d theta upon dt. What is this d theta by dt term? It can be written as tau omega. And we got mathematical definition of power. It can be written as tau omega. Again you can see the analog with translatory motion, when power can be written as F into V. So here F has to be replaced with torque and V has to be replaced with omega. So this is the instantaneous power, because I had used the expression P is equal to dW by dt. Now there is one more way so that we can define power. As you know, power can also be written as dk by dt. But here since it is a rotation, so kinetic energy has to be written as, in place of half mv square, now it will be equal to half I omega square. By now you are all comfortable with moment of inertia and omega. So moment of inertia we have to write in place of mass and omega in place of v. And we got kinetic energy for rotation, that is equal to half I omega square. So if I differentiate it, it can be written as I into 2 omega d omega by dt, and 1 2 is already here, these two got cancelled, so it is equal to I omega d omega by dt. And what is this term d omega by dt? It can be written as alpha, so that is I alpha omega. What is this term I alpha? Can it be written as torque? Of course. So this will be again tau multiplied with omega. So in a number of ways we can define power. It all depends on what is the situation, what are the terms provided in the numerical. So if it is given torque and angular velocity, we can use P is equal to tau omega. Otherwise, if kinetic energy term is given there, we can use P is equal to dk by dt, or if work done is provided, we can use P is equal to dW by dt. These all will lead to the same result. Now let us consider some examples based on these concepts. The first example is a wheel in the form of a disc having a mass m and radius r is turning at an angular velocity omega. First I am drawing the situation. It is the wheel having radius r, its mass is given as m, and it is turning with angular velocity omega. It is acted upon by a constant tangential force by the brake shoe. Do you know what is this term brake shoe? It is a kind of stopper here which produces friction against the rotation of wheel. So generally it is attached with a spring. This is what a brake shoe is, and with the help of this brake shoe, of course due to friction, a tangential force will be applied in this direction. Because omega I have taken as anti-clockwise, so frictional force F at this position has to be in downward direction, which is to be always tangential. We have to calculate the time taken by wheel to come to rest. Due to torque produced by this retarding force, of course after some time the wheel will come to a stop and we have to calculate that time. Now if we consider anti-clockwise direction as positive, then torque for F can be written as, because it will produce a torque in clockwise direction, so that will be equal to minus F into R, or I alpha, that will be the retarding torque, it is equal to minus F into R. From here we got value of alpha, that is equal to minus FR upon I. What is value of I? This is a disk. So about center it will be having moment of inertia equal to mr square by 2. This will give alpha to be equal to minus 2f upon mr. And initial angular velocity is already provided here, that is omega. So now we can apply the kinematical relation. Omega is equal to omega naught plus alpha t. What is value of final velocity? It has to be 0, is equal to omega naught is given as omega minus alpha, already we have calculated, that is minus 2f upon mr into t. From here we got t to be equal to omega mr upon 2f. So this is the time taken for wheel to come to a stop due to the retarding torque produced by this brake shoe. One more example here it is. A uniform rod AB of length L and mass M is held horizontally with the help of one light string and a hinge as shown. If string at B is burnt suddenly, find out the initial angular acceleration of the rod and the initial reaction force at the hinge. As we all know, at the moment of cutting off or burning of a string, the tension in string becomes 0. So that we have to consider here. Let us see how it can be solved. First, I am writing the forces acting on the rod. What forces will be there? Its weight has to be at the center, and here at the hinge, of course, one normal should be there. Let that be N. Since the string has been burnt, so there will be no effective tension at this point. But when string was intact, of course, one tension was acting at this point as well. Now since A is a stationary point, so we can apply Newton's second law in rotational form about A. And so if we write torque about A, that has to be equal to I alpha. What torque will be there? If I am writing about A, as you can see, for the normal, because it is acting at point A, so its torque has to be equal to 0. And then the only torque that will be effective is due to weight. So it has to be equal to mg L by 2. Tension already has become 0. So this will be equal to I alpha. From here we got value of alpha as mg L by 2I. What is value of moment of inertia about one of the end? That will be ml square by 3. 1 L got cancelled, m got cancelled, and we got this value to be equal to 3g upon 2L. This is the angular acceleration for the rod. Also it is asking for initial reaction force at the hinge. So it is asking for N. Now if we have to write linear acceleration of center of mass, that can be written as ACM has to be equal to alpha into R. And what is this value R? About A, center of mass is at a distance of L by 2. So this will be equal to alpha multiplied with L by 2. If I substitute the value, this will be 3g upon 2L into L by 2. L got cancelled, that is equal to 3g by 4. Now from rod's free body diagram, we can write for translatory motion mg minus n has to be equal to ma for center of mass, and from here if I substitute the value of A, N will be equal to mg minus ma, and A is having value 3g by 4, which will give mg by 4. So the normal reaction at the hinge when just string is burnt is equal to mg by 4, and the angular acceleration of rod at that moment will be 3g by 2L. Let us solve one example. Find the acceleration of the body if a force 8 Newton pulls the string at P that passes over the body and is connected by another string to a rigid support at Q. Radius of gyration is given here, that is equal to 2 by root 3 meter. Radius is given 2, and smaller radius of the inner sphere, it is 1 meter. Mass of body is also provided, that is 3 kg. We have to calculate acceleration of the body. So let us solve this example. First let us draw the situation as it is shown here in diagram. This is the inner sphere having radius r and the outer one having radius capital R, which is on a rigid support, and this point, which is the instantaneous center of rotation, is given here Q. What forces are acting? As it is seen here in the diagram, one external force is here, that is tangential to the inner sphere. Other has to be at the contact. The other force at the contact surface, let us consider that force to be T. So we can write here it is the T. Then first let us write force equation, that will be equal to F minus T to be mass multiplied with acceleration. And if we write the torque equation, let this C be the center, then writing torque about C, it will be equal to TR, which is our clockwise torque, and minus F small r, which is the anti-clockwise torque, and this whole has to be equal to I alpha. But as it is case of pure rolling, so alpha can be written as A by R. On substituting this, we will get TR minus FR to be equal to I has to be written, radius of gyration is given K, so value will be mk square. In place of alpha, we can write A by R. On solving these two equations, we will get F minus MA, this whole multiplied with R, minus FR to be equal to mk square A upon R. And again on further solving, A will finally come out to be FR, R minus R, and this divided by K square plus R square multiplied with M. On substituting all the numerical values, it will come out to be 1 meter per second square, which is our final short result. One more question I have. A thin uniform rod AB of mass M and length L is placed on a smooth horizontal table. A constant horizontal force of magnitude F starts acting on the rod at one of the ends. Initially, the force is perpendicular to length of rod. Okay, so rod has to be put on the table like this. It has to be vertically put. Now, if F is applied here, which is perpendicular to the length of rod, then we have to find distance moved by center of mass of the rod in time t0 and the magnitude of initial acceleration of end A of the rod. A is this point, so B has to be this. Now let us consider an arbitrary moment when rod has been tilted by some angle. Let's that angle be theta. So I am here drawing the situation. Rod has been tilted by an angle that is theta. What forces will be there? F has to be in horizontal direction, and of course weight has to be at its center. Let us write this center to be O. Now as F is applied in horizontal direction, so it will try to translate rod AB as well. Of course, this new position that I have drawn has to be somewhat horizontally away from the initial position, which was like this, right? And what this displacement has to be, because center of mass has been displaced by, let's that be xcm. Now I am writing acceleration of center of mass, that can be written as, because only one force is there in horizontal direction, so it has to be F upon m. If I write in vectorial representation, then it can be written as F by m I. This direction I have taken as x, this one as y. So displacement can be written as xcm, that will be half acm t0 square. And from here we can get the expression half acm is F upon m t0 square. So this is distance moved by center of mass of rod in time t0, which is our part A. The next part is initial acceleration of end A. Now acceleration of A can be written in two parts. It has to be acceleration of center of mass plus alpha cross RAO, because we can consider that center of mass is translating whereas other points are rotating about center of mass. This kind of motion we are going to learn in detail in our coming session. which is translation plus rotation involved. So acceleration of A can be written as acceleration of center of mass plus rotation of A with respect to center of mass, that I have written here as alpha cross r, and so its value will be equal to, already we have ACM, that is F by mi, plus alpha we have to calculate now. So alpha has to be, when we write about center of mass, torque will be equal to I alpha. What is torque of F about center of mass? It has to be F into L by 2, that is equal to, now the rod will be having moment of inertia about center of mass to be equal to ml square by 12 multiplied with alpha. So from here we can write value of alpha to be equal to minus 6F upon mlk. What direction this is? It is clockwise direction. Generally we take anti-clockwise as positive, and it is clockwise, so it has to be minus k, which is perpendicular to the plane of diagram. Cross RAO. RAO can be written as L by 2 and its direction has to be G. Now on solving this, the answer will come out to be 4F by mi, which is acceleration of point A. As you can see, it is the initial acceleration, and I have written torque also for the initial condition. So we got this second part as well. I hope you understood these questions fine. One small thing is remaining before starting a new kind of motion, that is rolling. This small subtopic is constrained motion of rotating rigid bodies, because it will be needed while during the numericals based on rolling. So let us see what is this constrained motion. Already we had read about the constraint relation in translatory motion, and here also some constraints are there. The first constraint is that of a pulley. So if we consider a simple pulley, what constraint has to be there? If this is the pulley, on in both sides the rope is hanging. Now here, since we are considering shape of pulley as well, so generally it will be hinged at the center, and if it starts rotating, then of course we have to consider that there is no slipping between the string and the pulley, which will be generally provided in question itself, that pulley and string surface is rough enough so that there is no slipping among them. So if we consider this kind of situation, the string is moving in direction with velocity v in upward direction and with some acceleration a in upward direction. The other part also has to come down with a, this also being the same v. What should be the direction of rotation for the pulley? It has to be in this direction, as is obvious from diagram itself. So we have to write v is equal to omega r, as we are writing that there is no slipping taking place. So whenever speed of string is given there, we can write omega for the pulley, and that has to satisfy the relation v is equal to omega r. In similar fashion, we can write a to be equal to alpha r, which is very useful while solving the numericals. Now we can consider a case in which a number of pulleys are there. Now we can consider that these are all coaxial pulleys, and let this be rotating in the direction shown with angular speed omega. Then for this kind of condition, we have to consider that omega has to be same, that is equal to that of the axis for all the pulleys. So this is again one constraint with the pulley. If one pulley starts rotating with omega, and if the pulleys are coaxial, then all have to start rotating with omega itself. This is another constraint relation. One more constraint is there, which is generally encountered in numerical problems, that is when two pulleys are connected like this, one bigger pulley and one small pulley. If they are connected with the help of belt or string in this manner, and let their radii are r1 and r2, let omega B, omega 1 and omega 2. Now see, what is the constraint here? Because if the belt is passing over both the pulleys, so whatever be speed at this position has to be speed at this position. If I am writing these positions which are in the contact of pulley 1 and 2, the points are A and B. For pulley 1, I have written this point to be B. For pulley 2, it is A. Then these two speeds has to be same. So we have to write VA to be equal to VB, because these are the points of a single belt or a single string which cannot be different. So if VA is equal to VB and that is equal to some common value, then of course we can write that omega 1 R1 has to be equal to omega 2 R2, which is very important relation through which we will get one equation while solving the numerical problems. So far so good. Today we learned about work done, about power, and then some constraint relations in rotation. In next session I am going to discuss about one more thing, that is rolling. So let us look forward for it. Bye.